Okay, good evening everybody. I hope everyone's having a wonderful day. So, I want to pick up from where I was last day. So last day I introduced you to the definition of big O. So this is the formal definition. So up to this point you may have seen big O before, but maybe not necessarily its fancy-pantsy definition or formal definition. So if ever you find yourself wanting to ask if one complexity function is big O of another, this is the definition you could always come back to if you ever want to check. So as you play around with this definition and some of the properties that you can have with a lot of the counting rules we have, you're going to build, I'm hoping that by the end of this course, you'll have some basic intuition of how different operations will cause and increase the complexity of an algorithm or a data structure. So we're going to see a lot of different ways where that's going to happen, whether it be through iterative structures like our nested loops or just a single for loop, or through, for example, recursion, which will be another important tool for how we describe algorithms in this class. So anyways, I want to reiterate this definition. So if I give you two complexity functions, f and g, I'm going to tell you that f is big O of g if and only if there exist these two constants. There's c, which is a positive real number, and n0, which is a positive integer, such that when you have these two constants, it has to be that this inequality holds. This f of n is less than or equal to c times g of n. This has to hold for all n greater or equal to this n0. So notice that these two constants, they play a very important role. But here's the thing I want you to really pay attention to. So I'm going to underline a couple of things I really just want you to really just keep in mind and keep it in the back of your mind as we're talking about this, because it's going to come up a lot. So there's this there exists part. And when I talk about that, I talk about these two constants. So once I know these two exist, I would like some way to check this. And what do these two constants relate to? They relate to this inequality right here. But it has to be that this inequality is true for all n greater or equal to n0. So you're going to find that when we start actually trying to prove claims about big O, that the game in town is going to be that we find these two constants, the two I circled over here. And then my job is just to check that that will indeed work. It isn't just simply I plug in n and it works. It's actually that I have to perform some basic argumentation to verify that, and I pick those two particular constants, that this inequality will always be true for over all of those values when n is bigger or equal to n0. So we're going to see an example in a moment using some more basic techniques, and I'm going to show you some neat counting tricks you can use to simplify this process. So before I proceed, I want to talk about a couple usages of big O. So there's kind of two things I want you to keep in mind about, because when you talk to different people about big O notation, sometimes it's very useful to think about big O in a couple of different ways. So the first way is you can think of it like I'm talking about what is called a set. So it's a big collection of complexity functions. So if you've never seen this E symbol before, I've used it a few times here at least. I may have used it before. Remember, this means in. So if you ever seen set theory before, don't worry too much if you have or have not. This just means in. So I'm saying this function is in, or is, big O of g. What does that mean? That means that big O of g, this big O of g right here, this is actually a collection or set of complexity functions. So that's one way you can interpret big O notation, is that when you measure out all those operations, you end up with a complexity function. It may belong to a whole collection or set of complexity functions. What's that set? If I know that f is in big O of g, then I can tell you that it belongs to this set, big O of G. So I'll hopefully be able to show you an example of this maybe later. So I will include the notes if you find yourself looking for or just vying for a formal definition of this. I will have that in the notes. But for your purposes, the big thing I really just want to make sure you are aware of is that big O is actually can be thought of as a set of complexity functions. In contrast, another usage for big O, so if you want to get really formal with big O notation, you can talk about everything in terms of sets. The other usage, this is one that's rather useful when you want to simplify calculations. So let me talk a little bit about this one first. So I must stress, when you see this equal sign, and I must stress again, this may be a little bit confusing because there's been several times where this thing about the equal sign has come up, and I want to make sure I'm very clear about this. When you see the equal sign in this context, this is a convention. When you see the equal sign here, it's not an equal sign. When you see that equals right there, read it as is. Just like I have over here. So usually when somebody talks about, here's my complexity function, f is big O of G, or f is in big O of G, either one is a pretty common way of saying these things. But I must stress that it's a very common convention among computer science circles to use this equal sign for is. So if you don't want to write the word is, you can use an equal sign like this, but I must stress, it's not an equal sign. I'm going to show you why and how this often gets used. So I'm going to mention that this is common for simplifying calculations. So I'm going to do an example just to illustrate my point by this. Well, so excellent question. So somebody is saying one is f in big O of G. So often when somebody reads this off to you, they'll say, oh, f is in big O of G because it's a member of G, like big O of G. Not to be confused with G itself. Remember, G itself is a complexity function. But yeah, these are, if somebody gave you this, and somebody gave you this, and somebody gave you this is right here, all of these are the exact same thing, just to be very clear. There's just different ways of writing the same thing. So you'll find very often, I like to go back to using the word is sometimes, if I'm really just unclear for the reader. I like to make sure I just go back to just saying is if needed. But if I need to talk about it in terms of a collection of functions, I'll often will use this set theoretic notation, or sometimes I get into the habit of that because it's a very formal way of talking about the big O notation. If I find myself doing a lot of calculations with big O, I'll often adopt this notation because it's really helpful for simplifying calculations. So let me show you an example of what I mean by this. So suppose I have three complexity functions. Suppose I have f, where f is 5n squared plus 30n plus 20. Now I have a question for you. If I wanted to know the big O notation, so I want to know what the big O should be, what the g would be in my definition up here, what would be the smallest function you can give me for this function f? Could somebody tell me what the big O is for this one? Any ideas? Yes. So notice that. So there's two things I want to point out here for you. So I will give you a couple of simple rules just to recap how we could easily calculate that. Most certainly, you'll notice that the way I wrote this, so this is what the function f is for input n. But notice the way I use the is here with this equal sign is it's one directional. It goes from left to right. It doesn't go right to left. But notice that I've made my calculations a little easier by just simply suppressing all of the stuff that isn't important for me. We're going to see that when I pull out some more functions to play around with, okay? So far we're doing good. Now suppose I give you another function. We'll call it g, not to be confused with that g up there. We'll call it 2n cubed, so it's going to be 2n cubed minus 5. Now, can somebody tell me what the big O for this one is? So g is 2n cubed minus 5. Yes, it's n cubed. Very good. Very good. Now, you might ask, Dan, how do you figure that out? Well, that's why I'm giving you this definition. It's rather helpful for doing this. So far we're doing good. If I give you h, if I tell you it's just 4n, what's the big O of that? Yeah, it's just n. Perfect. See, you guys are pros at this. So now here's where this notation becomes rather helpful. So I'm just going to need a little bit more space. So I'm going to write it across this way. So suppose then, if I have these three here, if I write f of n plus g of n plus h of n, now, each one of those, I figured out the big O for each one, right? So what I'm going to do is I'm going to substitute in F, G, and H all with those big O notations. But the big thing I'm going to point out to you is that we read it always from left to right. It doesn't work when you read it right to left. It's always that it subsumes or simplifies as we move to the right. So that's why I'm saying it's not like an equal sign. An equal sign should be true regardless if you read it from the right to the left or the left to the right. So here you're going to see what I mean. So I'm going to replace f with big O of n squared, because that's what we said before. G, well, that's big O of n cubed. And the final one was big O of n, one for h. So here's what I really want to hammer in. This notation is rather helpful when you have a whole bunch of parts to your algorithm to analyze. So in this sense, it's a little bit more informal the way I'm using it, because the first thing I need to point out again and remind you of, and this is technically an abuse of notation in the way I described big O earlier. But I'll come right back to that in a moment. So now notice that I've replaced f, g, and h with big O of n squared, big O of n cubed, and big O of n. Does anybody have any ideas of what the big O should be after I look at all three of these and I add them like this? I'll give you a hint. It won't be much different from what we just did a moment ago. Yeah, it's big O of n cubed. Very good. So all you do is you just take the one as the dominant term. Now I want to explain why this is why you might think of it like this. Okay, you know how I did worst case analysis the other day, and I came up with a complexity function. Well, you can imagine f as being, say, maybe I have an algorithm that has three phases to it. It first performs this first phase. And say the complexity, if I count up all those operations and that was f, I could tell you, for example, if this was the complexity function, I'll tell you it has big O of n squared operations that are performed. Then I look at g. Suppose this is the second part of the algorithm. And I tell you, okay, that takes big O of n cubed operations. And then I have my third part. Suppose it's the part that cleans up things at the end. And that is big O of n operations. What I'm telling you is that this allows you to simplify down your calculations, so you don't have to worry about, okay, the first part you have this many operations, the second part you have this many operations, and the third part has this many, and you have to like combine all of these and simplify. So because the way that I've shown you previously would be that I would take this, add it to that, add it to this, before I even get to big O, right? What I'm telling you is that you could even dissect it like this into parts, keeping in mind that none of those pieces are related to one another. And you can apply the rules that big O just like that. to calculate the overall running time of your algorithm. So do you see how this simple notation can save you a little bit of time when you're trying to jot down some calculations? Yeah, so we're taking the most dominant term among the three I have here. So I have n squared, n cubed, and n. The cubic term wins here. Yes, so I'll be talking all about some of these little rules in a moment here, but keep in mind that we're going to go a little beyond that. I'm actually going to start showing you how we can actually use this definition to prove these things. So why should we take the dominant one? I'm hoping I'll address that in today's lecture. So I don't want to give you a hard and fast rule. Instead, I want to convince you that it in fact is what you could do. So I'm just giving you this as an example of usage. So yeah, it's the dominant term here. So notice that, so the first thing I want to point out and remind you of is that first, you have these several usages of big O. Remember I told you before that big O is also a set. Now for those that are inclined to think about types, you might say, Dan, that doesn't make any sense. How can you add over two sets like this? That doesn't make a whole lot of sense. And it doesn't, right? It doesn't. You would have to define this in a little bit more of a special way to do that. So that's why some people in some circles, like mine, some people would tell you that this is an abusive notation because I'm using these sets like if they were algebraic terms, like variables, which they're sets. So just keep that in mind. So again, it's very useful for simplifying down calculations, but most certainly, if you find yourself just really nitpicky about doing this kind of stuff, you can always fall back to just the definition or thinking about it as a set of functions. And this set of functions, by the way, has a very meaningful representation I'm hoping to touch upon either today or on Tuesday. So, are there any questions about these two common usages? I just want to make sure you're exposed to this because in some circles, they like using this 2 version. Some people like to use 1. I'm a big fan of 1 personally, but for this course, we're really focusing around this definition. So if you find yourself cozy with that, you can use that. If you want to do this, that's also okay. I'm not picky about it. So anyways, are we okay with this? So question. Does it give us an exact time the algorithm takes or just an estimation? Now, you got to remember back to the kind of the big picture look of this whole thing. The big picture. Because remember, our measurement of time is based on the model of computation. And the model of computation counts operations based on whether they're simple or primitive versus those that aren't. So what we did was we count up all of those operations, right? And in our model of computation, that when we add up all those constants, we end up with a complexity function. And that's going to be a measurement of, for example, the time that it will take. But remember, that time is based on the model of computation. And there are some very natural ways of thinking about those constants like I mentioned the other day. For example, when I showed you that example where I had the table, for example, you can take that and rearrange it by its operators and still end up with a linear function when we looked at linear search. You can actually do that. And those constants could quite literally represent CPU cycles of a computer. So I must stress, the actual calculation of the CPU cycles, that's a machine-dependent view of things. We're trying to kind of take one step away from that, at least, and we want to actually understand the efficiency of the algorithm itself, or the data structure's operations themselves. So I'm hoping that will clarify kind of the big picture here. How would you show these calculations using 1? So that's a wonderful question. Usually people don't ask me about this, so I'm very happy somebody asked me about this. So you'll notice that every time I add here, this is helpful for me when I'm dealing with certain key operations, like if I have phases to an algorithm. Now, when you're dealing with a set like this, now this isn't really a course on set theory, but sometimes sets do come up every once in a blue moon. If, say, for example, I give you like big O of G, you can talk about big O in terms of subsets, So say if there's another function called h, for example. So if I knew that g was a subset of h in terms of big O, so I have this set of complexity functions and I have this set of complexity functions. The way you can visualize this as a diagram is you could imagine that f is sitting somewhere. So this is f. The f sort of melted here. So this f is sitting inside of big O of g. And big O of g is sitting as a whole inside of big O of h. So it's actually just a set of functions. So f would be just a member of big O of g. And big O of g itself is actually just a subset of all of the elements that are in big O of h. And these elements are complexity functions. So you can actually describe these things in terms of sets, but I'm not going to get into that detail here just for the sake of time, but I'm happy to answer any questions about this if you find yourself curious about it. But does that answer your question? So yeah, it does make things a little bit trickier to do because you'll always have to really talk about the functions themselves in the way that we talked about them earlier. You know how I said, okay, you take all these, you add those, you add those, you add those. You probably will have to do something quite like that. But like I said, it's about the finesse of your analysis. Sometimes you find a very clever way of writing it out. That does happen very often. But yeah, there's some people that are very fond of one. Some people are fond of two. Some people just say, whatever works best. Some people just say, yeah, it's just, there's a definition. That's cool enough. So, let's talk a little bit about some basic rules around big O. Some of these you may have seen before. If not, I just want to reiterate them. These are going to work well enough for most cases we're going to run into. But every once in a blue moon, you're going to find that some of the complexity functions we're going to deal with are not going to fall very easily into these rules. And then we'll talk about some classes of complexity functions. Now you might ask, what's a class? It's just a fancy name for our purposes as a bunch of sets that all have the same type. So here are some basic rules. Rules with big O. So these are some rules you may have seen, you may not have seen, that's okay. But remember, these are just hard and fast rules. For most cases you run into, this will typically work. But in this course, you have to be very careful about it, okay? It isn't just going to be as simple as just when you come up with the complexity function, it may not necessarily be just right there looking at you in the face. There's going to be some cases where it's just going to be where you count up the operations and then you realize, oh yeah, there's something else going on here. What is that thing that's in my complexity function? I have to examine that more carefully. But you'll find most cases when you're dealing with polynomials, for example, most of these rules will apply. So the first one I want to mention is that you can drop multiplicative and additive constants. And the key thing is that they're constants. They have to be constants. So just as an example of this, if I give you 5n plus 3, notice that there's a 5 sitting in front of the n, and I have a 3 just sitting right there. And if you ever find yourself just asking, okay, is it true that this, and I'll tell you up front that this is big O of n. And you might have thought about that before I even wrote it down, right? And so what I'm saying is that you can just basically ignore that, and you can ignore this. So when you see multiplicative constants like these and additive constants, like my 3 over here versus the 5, you can drop these. So that's one basic rule. Another one is consider the most dominant. Now you might ask, okay, so Dan, how do I determine the most dominant? We're going to talk about that in a moment. The most dominant term in the expression. So just to be very clear, and almost all the time that you're going to deal with this, you'll see quite quickly what it is. So if a polynomial, which I'll talk to you about polynomials in a moment. If a polynomial, take the highest degree polynomial. Now you might ask, Dan, what is a highest degree polynomial? What I'm saying is take the one with the biggest exponent, okay? The one with the number that's the largest one at the top. So just as an example, if I give you 8n cubed plus n squared plus n plus 1,000. Now don't let this 1,000 throw you off. It's still a constant, right? But notice I have an n here and I have an n squared. Well, I already told you you don't have to worry about these constants, right? And then you just pick off the dominant term. In this case, notice I have an n cubed right here. So I would just tell you that this is big O of n cubed. So for a lot of cases, often these two very simple rules will be enough. But remember, these aren't proofs. These aren't ways that I could tell you that is indeed the case, that it's big O of n or big O of n cubed. They don't actually tell you some way to actually check this. So that's the point of today's lecture. Today's lecture, I'm going to show you actually how you can show somebody that it is in fact the case. Does everybody understand that? So you may know some of these simple rules, but the goal at this level is really to say, okay, if I give you some complexity function, could you show me why it's big O of that thing? So somebody's asking, if the complexity function is 5n minus 3, can we deduct the 3? Yeah, it's just an additive constant. I must stress that often we'll be just restricted to so-called complexity functions. So the functions we'll always play with are going to strictly be non-negative, which is very natural when you're counting operations, because the idea of having a program that does negative operations for small inputs would be very strange, right? If we have something like n squared plus log n, would that be big O of n squared? That's a much more interesting question. Actually, both of those are good questions, by the way. But this one in particular, I'm hoping I'll address this in a moment. But in that case, somebody's asking, oh, if you have n squared plus log n, would it be big O of n squared? And the answer is yes. The answer is yes. So I'm going to give you kind of a layout of how you can organize these complexity classes, the complexity functions by class, so that you know which ones are more dominant than other ones. So let's talk about that, okay? Because it's nice to know that some functions have, so if I talk about big O, there's going to be cases where you're going to have, say, polynomials with different exponents, but you're also going to have other kinds of functions, like exponential functions. And you might ask, okay, so which one dominates, at least in the terms of these rules over here? I want to talk about which ones, if you go back to my picture, somebody asked that lovely question about subset theory, where which ones are contained in which other ones in terms of sets. Because remember, big O, you can think of it as a whole bunch of complexity functions, where each one is like in the next class, just like, almost like a nesting doll. So I'm going to talk about this. And once you see that, it makes things a little easier to kind of play around with. So I'm going to say some common classes. Now, if you remember, like I said, a class, in the context we're going to use it, is just simply, if we're talking about several classes, we're talking about a bunch of sets of the same kind. So in this case, they're sets that contain complexity functions. Some common classes of complexity functions include, so some of these you may have heard of, other ones may be a little bit more mysterious. So the first one I'll tell you about is big O of 1. You may have heard of this one. This is we would refer to this as constant. The way you could tell right away is that you'll notice there's no n in here at all, right? It's completely independent of, say, whatever the input would be, right? So functions like where the input is 5, for every n, the output would be the number 5, for example. That would fall into this set right here. So if you can get an algorithm that runs in constant time, for example, that's really fast, because notice that if it was, say, big O of n, that would depend on the input size, right? But here, it doesn't depend at all on the input size. So that's the first one. The next one, so the big thing I want to point out is that I'm listing them by order of containment. By containment. So I'm saying is that whatever I list as I go down, all of the complexity functions that belong to this set of complexity functions are all going to be in the next set of that's going to be directly below it. Like I said, it's going to be like a nesting doll of functions. So next you have the logarithmic functions. So if somebody gives you an algorithm that runs in big O of log n, they would say that the running time is logarithmic. Next one is big O of n. You might know this one at least. Linear. So if somebody gives you a running time where it's big O of n, and n is in fact the input size, they would say that this algorithm runs in linear time. Okay, how about n log n? Has anybody seen big O of n log n before? Obviously, you've seen log probably, and you've seen n. It's just the product of those two things. Some people give this a name. I find in most circles, you'll just say, oh, it's big O of n log n. Some people like to call this log linear. So you can see it just contracts the first part of logarithmic and takes linear. Log linear. But I'll tell you up front that most people, when you talk about running times of these, most of these would just be, they'll just tell you it's big O of n log n. Is this the one used for binary search? No, actually, if you want an example of an algorithm that runs in big O of log n time, binary search takes big O of log n time. Versus linear here, you might know, remember our linear search? Linear search runs in linear time. But we will be seeing in this course algorithms that are going to run in n log n time. So we're going to see some examples of these in this class. I know another one that you may be familiar with is quadratic, big O of n squared. So quadratic. For example, you might know an algorithm that runs in big O of n squared. You might know, for example, insertion sort. Insertion sort runs in big O of n squared time in the worst case. So now we're going to go a little bit beyond. So now we're going to really widen the bubble of how many functions we're going to be describing here. So just to remind you, just to give you a big picture look of this. So imagine I have this, like a circle here. Everything that's in this circle, I don't know, it's technically an oval. It's kind of a melted oval. It went in the microwave and it kind of got a little oblong there. So all of these functions are big O of 1. So for example, a function like 2 or 1, then all of those are going to be contained in big O of log n. Then all of those are contained in big O of n. Then all of these, okay, now I've just kind of given up on the circular-esque shape. Let's just fix that. This would be big O of n log n. And then beyond that, I'm sort of running out of space. I'm making sound effects as I'm doing this. All of those are contained in big O of n squared. So the thing I really want you to keep in mind is big O is an asymptotic upper bound for our complexity function. So if you have a complexity function that, say, is linear, it most certainly will be in big O of n, but it also will be in big O of n squared. So I must stress that very often when we study and use big O, we always have to think about what's the smallest function among these classes that it fits best into. So I must stress that you could say all sorts of really funny things with big O notation. Just as an example, you might know, like we talked about binary search over there. I told you that binary search runs in big O of log n time, right? That's what I wrote over there. With our definition of big O, with the mayonnaise, the formal definition of big O, you can also prove to me that binary search runs in big O of n to the 99. Now I have a question for you. Is that a very accurate way of describing the running time of binary search? No, right? It's an asymptotic upper bound. So I must stress that when we describe our running times for our algorithms, we don't want to give really nasty looking things like this because they're not accurate, right? That's why when we do our time complexity analysis, we try to be careful about how we count the operations, and two, how we categorize them in terms of this big O. So you would not want to do this. In fact, in CS 340, you will see more asymptotic notations that will force it so that it has to be big O of log n. An example of one of these is, for example, something called big theta notation. For big theta notation, you wouldn't be able to get away with saying this about binary search. But we're not going to talk about big theta here. So that's my point about the containment of these. Does everybody understand my point about the containment of the functions? So for example, if I have another function, like say if I have n plus 1 here. Like if I have n plus 1, it belongs to big O of n. But it also technically belongs to big O of n log n. Actually, sorry. This should be in here. N plus 1's there. But the point is that it's like a big nesting doll. So we're going to see how this plays out as we talk about different running times of algorithms. Can I say big O of log n is in big O of 1? The answer is no. And I'll be giving you some tools to do that today. So anyways, with that being said, and I must stress the main reason why you can't get away with doing that is the functions that are big O of, say, log n, for example. These are all of these functions. Sorry, not those ones. These ones. Those are all of these ones I'm just shading in, but they're not the ones in the innermost part necessarily. Some of them can sit out here, but other ones might be in here too. So if I pick out, say, for example, say there's a function right here, say if it's 2 log n plus 1. This most certainly is not a constant function. The point is that I'm telling you that the order in which I'm providing them to you is the containment of them. So for example, if I give you a function and it belongs to big O of n squared, it may not necessarily belong to any of the ones I describe above. However, some of them might. That's the point I'm making here. We're going to see this as we play with these things throughout this course. So another one, this is a much broader collection of complexity functions, is the polynomials. So if I give you a constant, c, and it's greater or equal to 0, this would be big O of n to the c, where c is a constant. So this is a much wider set of complexity functions. For example, this will contain all the complexity functions that belong to actually all of these. In fact, it will be, for example, if I make c is equal to 2, you end up with quadratic, right? If it's 3, it's all the cubic ones. But it's for every constant. So for example, just to be very clear, because of what I just described, because remember, big O is going to describe an asymptotic upper bound. And I'm going to talk much more about this in a little bit. So if I give you something that runs in big O of log n time, which means it's some complexity function, it is big O of log n, it also has to be the case that it is and runs in polynomial time, because big O of n to the c will contain any function that's in big O of log n, because all of those are going to be in big O of n. Like I said, it's a big collection of all bunch of complexity functions. So these are generally, all of these above here that I've just described to you, often when you talk to your typical person that studies this kind of stuff, if you're studying interesting problems, usually anything above this line, people will often call efficient. But it always depends on the problem at hand. So for example, some problems are much easier than other problems. For example, we have an algorithm for solving the search problem with an array, like we have linear search, right? Linear search, like you could solve it in linear time. The question in that case would be, can you do it any faster? And we're not going to really talk so much about that in this course, but if you take CS 340, you might be able to see that. But the point is that for different problems, what efficient is can be a little bit more narrow depending on what the problem is. However, generally computer scientists, if you talk about efficiency in terms of there's an efficient algorithm or there's no efficient algorithm, usually the line is drawn at polynomial. Anything after this is going to be just a little bit wild with its running times. So just as an example, the next one on the list is big O of c to the n. This is your exponential functions. So these are where you have the constant c greater than 1. So this contains, for example, so if I make c is equal to 2, you end up with big O of 2 to the power of n. So these are complexity functions that grow so fast that if you gave me any one of these, it's like no competition between the two. These ones are going to grow much slower than the exponential functions. So when you give me an algorithm that runs in exponential time, it's going to be quite a bit trickier to say that it runs quite efficiently. Unless it's a really tough problem. Since it's c is greater or equal to 2. Previous one on the list. So I must stress that I also want to allow it to also be something like 1.44 to the power of n, for example. I just want to make sure it's strictly bigger than 1. Otherwise, it will not start partaking in what we call combinatorial explosion or exponential growth. So I want to make sure it's at least bigger than 1. As long as it's bigger than 1, we're okay. But does that clarify the question about why I made it c is greater than 1 as opposed to it being quite similar to the one above there? But yeah, you technically, in the way, if you feel like you want to make it so it's c is greater or equal to 2, that's also okay. Oh, for the polynomial. Now, I made this c is greater or equal to 0 because, remember, this is for any c. So that as long as this exists, we say it runs in polynomial time. So, for example, if you give me a quadratic running time, that's when c is equal to 2, right? So the idea here is that it runs in big O of n to the c for some constant c greater or equal to 0. So it's not just that it's just some, it's that it has to exist. That's what I'm trying to say. Yeah, no worries. It's a much broader collection of complexity functions. So you give me a function, as long as there is some constant that takes on this form, you could say it takes polynomial time. C is equal to 0. If I make it n to the 0, that should just be 1, right? So if it's c is 0, then you end up with a constant function. When you have it as c is 1, you end up with a linear function. When c is 2, you end up with a quadratic function. When c is 3, you end up with a cubic function. But the big point here is that it's the whole collection of all possible polynomials. That's the point. So it could be something with an exponent with the leading exponent is a 4 or a 5 or 10,000. The point is that it's some polynomial. And by the very similar rules that I gave over there, you can always simplify them down so they fit into this category. Yes, that's, so just to clarify, somebody's asking, so for the quadratic as well, I could say it's big O of polynomial. So yeah, so if you told me that your algorithm runs in big O of n squared, that is indeed polynomial time. The main reason why I'm saying that is because of the big O. The big O is always going to operate like an upper bound on the running times from an asymptotic standpoint. So that's why I'm saying you can order them like this. So just like if I were listing out these as numbers like 1 through 10, for example, I don't know how many categories I got here, but the point is that if I have 5 pixie sticks versus 4 pixie sticks, you could still give me 4 pixie sticks if I have 5 of them. That's the point I'm getting at, is that each of these subsumes the other category. So it sort of just absorbs it like a blob. Are there any other questions about this? So I just wanted to make sure we got kind of a lingo to talk about different complexity functions. So you know which ones are the ones that are like, oh yeah, these are the really fast. It's like these are ones that you're very desirable for an algorithm. The ones way down here, not so much. It depends a lot on the problem at hand. In fact, I'm going to write 2 more here. These are the ones with really nasty growth rates beyond even exponential. For example, there's factorial. Even for a sufficiently large n, the n factorial grows so fast that it'll even make the exponential look kind of like a little, like if you had like the little like Chihuahua dog versus like, I don't know, a German Shepherd or something, that's like the gap can be sometimes quite big. Just like that gap also persists with polynomials versus exponentials. So yeah, you can think of it like orbits, for example, of containing all of those that are within the orbit. Yes. So another one that I'm going to point out to you that is much further out, even further than this, is big O of n to the n. I don't usually have a name for this one. It's just, if you had an algorithm that runs in big O of n to the n, it's going to be really, really... It's what I call an oops. You don't want that. Unless your algorithm is really that slow and it's necessary. There's a very select few problems that kind of fall into that category, but they're really out there. You can call it oops, but I don't think that's the technical term for it, but I don't usually give it a name. It's just, you will not very often run into that. So anyways, with that being said, these are some major categories that I want you to be aware of. So whenever you see one of these, I'll often will describe them in words, or I may actually use the big O directly. So just be aware of these. So anyways, I want to talk about proving big O claims, because that's going to be kind of the big thing for this lecture. So let's plow ahead here. So I want to first start off by really kind of motivating how we can go about proving these big O claims. I'm going to start off with some basic algebraic techniques, but I want to really kind of hammer in that this first approach isn't really the one I'm going to recommend, but it does work, but it requires you to have more assumptions about how your functions will operate. Sorry, how your functions operate. For some reason, it sounded like I said cooperate. I meant operate. So let's talk about showing f is big O of g. So suppose I want to show that if I give you some function, I want to know if it's big O of g, and g is the ideal function I want to categorize into, for example, from one of those over there. So let's consider an example. Suppose that f is 2n, and g is n squared. Now, the first thing I'm going to do is I'm going to attempt to chart both of them out so that we can kind of get an idea of how both of these operate. Now, I must stress that a picture like this is not a proof. So, just to be very clear, I'm just using this to motivate what we're up to. So, you get to enjoy the pleasure of me drawing a really bad picture. So, I'm going to plot out the two functions here. So I'm gonna label my axes. Now, I don't know if I have enough ticks here. We're gonna have to be careful here. Let's see, 2, 4, 6, 8, 10, 12, 14. That'll be good enough. That'll be good enough. And I'm gonna have this starting at 0. Then I'm going to have 1, 2, 3, 4. So on this side, the horizontal axis is gonna be n. Then I'm going to plot out the two functions along the y-axis. So let me just lay out these two. So I'm just going to cross my fingers I can draw a straight line for you today. I'm just joking around, just to be very clear. But I assure you, straight lines, that is not something I'll test you on the exam for, okay? Don't worry. So anyways, if it's 2n, it should be just a straight up diagonal line on this, assuming I drew this properly. It should be something... Oh, poop! I failed, man! So that's our straight line. It's our straight line, so it's 1 matches up with 2, 2 matches up with 4, 3 matches up with 6, and 4 matches up with 8. That's good enough for us. So this is f. And then we're going to have g. Now, g is a quadratic. So you know it's going to look something kind of like, let's see. Should be kind of like something like that. So this is g here. So there's f and g. Is there anything special the derivatives or integrals of these mean? Now, here's the cool part. Sometimes there are, but I'm not going to talk about those, and we don't actually even have to go that far. But you most certainly can use, for example, limits to talk about some of these things. So, anyways, there's kind of two pieces here I want to talk about. So I'm going to try charting. So this is my chart. This is beautiful. It's a beautiful chart. So I want to know, remember back our definition, there's the point n0 where one function is going to start dominating the other function. Now in this case, since I've charted them out, you can clearly see at what point g dominates f. And I must stress that when I say dominate, that means that after that point, n0 in my definition, one function will surpass it in terms of its output value. So does anybody have any ideas about what would be where n0 might be? Where's kind of the smallest value for which n0 can be, based on the definition I gave you? So remember, the inequality that we're looking at is f of n is less than or equal to c times g of n. And I want it to be true for all n greater or equal to n0. Yeah, 2. So 2 is a very natural place to pick. Okay, it's a little crooked, but please don't get too upset with me. So n0 is right here. Now notice that I could have picked n0 at 2, or I could have picked n0 any point after this. But every point after that, notice that I can look at f here, and I look at its output for a given value of n, and it most certainly will be the case that it's less than or equal to g, right? The only thing on top of this is that constant c, which, like I said, one intuitive way of thinking of that C, at least in terms of algorithm analysis, is that that usually represents your constants or the speed of your operations. But keep in mind, from a mathematical standpoint, that C is just a constant. It doesn't have to have an intrinsic meaning. So the point is, it doesn't matter how many multiplicative factors there are. In this case, in fact, you can just inspect this and say, hey, look, if I make C is equal to 1, notice that this inequality will work regardless if I pick n0 to be 2, right? So the two big things I want to point out to you is that when I establish a big O claim, I need to find C and I need to find n0 such that this inequality is true for all points after n0 and at n0. So everywhere after this point, it has to be that for whatever the multiplicative constant is times g, it has to be that that part on the right-hand side has to dominate f. Is that clear, everybody? So that's going to be the big game plan here. And you might ask, Dan, do I have to plot these out or anything? The answer is no. In fact, almost every technique I'm going to show you involves very basic counting. So I'm hoping this will be rather helpful. So if you wanted to, you can take what I just plotted out here and you can algebraically verify what I had said over here about those two constants. I'll leave you for that. I'll let you read that in the notes, but I'm going to suggest a much simpler way of approaching these kind of things. So in this case, what you could have done is you can do something like root solving, for example. So just to clarify, you would just treat the inequality like an equation. So that's one way you could have determined that point for n0. In fact, you could have just algebraically manipulated it, done something quite similar to in a calculus class. So you could have done it that way. And that technically works, but remember, one thing you have to watch out for when you do things like that is you have to take into consideration the behavior of your functions you're playing around with. So, for example, there's some things from calculus you know about quadratics versus a linear function, about how fast each one grows with respect to, for example, a derivative. So these are things that you know off the backhand, and you know that you can use those assumptions about which one increases faster, for example. But I don't want to use a lot of those tools right here. I want to show you some simpler counting techniques for doing this. So let's do some examples. So notice the big game plan here. I'm going to try to find these two constants so that this inequality holds, and it has to hold for all n greater or equal to n0. And like I said, n0, there could be many, many choices for n0. There could be many, many choices for C. In some cases, there may even only be one pair of those two constants that work. In other cases, there may be infinitely many. So good. That's a good question. So could we ever justify a slower algorithm if n0 is like 1,000 and we intend to use data sets lower than 1,000? That's actually a really lovely question. I like that question. So if you had it where, say for example, you're comparing two complexity functions and n0 ends up being a really big constant, this is actually a practical consideration to take. So if you have, for example, information like that, where you know that you're never going to have an algorithm where it's going to be that big for the input, that is definitely a practical consideration you need to make. For example, if you know that your instances are never going to be more than 1,000 in terms of their size even, or 10,000. These are things to keep in mind in practice. But at the same time, also remember that if we ultimately want to know which of the two algorithms is efficient for all problem instances, it's okay if n0 is really big. But I must stress that usually n0 is usually very small. But like I wanted to say this, is that n0 in some very limited circumstances has been shown to be rather big, but those are way beyond the context of this course. Sometimes you'll have it where some of these constants that you get from your complexity functions are rather large, and they could actually influence the practical implications of using it or not. There are some instances where we'll run into that. I may have some time to discuss some examples of these later on in this course. That's a wonderful question. I like that question. So I want to do some examples where we actually pick up that definition and we use it. So is that okay with everybody? Let's proceed if that's the case. Okay, so let's proceed. So I'm going to kind of plow ahead with some examples. I'm hoping and crossing my fingers we can get through everything we need here, because we sort of talked about a bunch of other things that a little longer than I was anticipating. But that's okay. Let's proceed. It's sort of the fun of lectures, that it's not just lecture with me, it's lecture with everybody. That's the one thing I really want to make sure it's clear for everybody. So let's do an example. Let's start off with something that seems rather cute looking. So let's start off by show. Let's try showing. Let's show n plus 5 is big O of n. So we're going to start off with this being f, and that's g. G is sitting right inside here at the big O. So I'm going to try to do this. Remember, I'm going to pull out what the definition tells me. Remember, the definition tells me that there exists C and N0. Remember, C is a positive real number, N0 is a positive integer. And our goal will be to establish that inequality, f of n is less than or equal to c times g of n for all n greater or equal to that N0. So normally when I do this, I lay out a game plan. So it's usually a good idea to describe to the reader what you're doing. So that's what I'm going to start off by doing here. So I'm just going to say we need to find constants. C, which is C is a positive real number, and N0, which is a positive integer, such that, so all I'm doing is I'm just plugging in the definition, such that for all n greater or equal to N0, n plus 5 is less than or equal to c times n. So do you see how I laid out the game plan? So I tell you, we're going to find these two constants. That these sort of decided to hang off, kind of like a piece of melted butter off a cob of corn. So I'm going to find these two constants such that this holds for all n greater or equal to N0. So that's going to be the game plan. And now keep in mind that once we find and justify these two constants, we invoke the definition of big O at the end to establish and prove the claim. Okay? Because remember, we're using the definition to establish this. So you might ask, Dan, where do you get these two constants from? Well, like I said, you could algebraically play around with everything and figure them out, but that can sometimes be very timely and costly unless you're very analytically minded. But you'll find that a lot of the techniques I'm going to show you here and probably next class will be really helpful for doing this. So let's talk about this. So if I have n plus 5, what I would like to do, so this is sort of the strategy I'm going to start off with. I'm going to try to make this right-hand side of this inequality look like what's right here by trying to imitate terms that I have on the left-hand side so that they're written in terms of things I have on the right-hand side. It sounds really strange, but I'm going to hopefully convince you that this technique is really straightforward to apply for most things you're going to run into. So here's what I'm going to suggest. So there's a couple ways you can go about this. The easiest way of doing this is, keep in mind, like I said, there's many constants that work. One thing you could do, and I'm going to stress that in the notes, I'm going to show you how you could do it with a different pair of constants, just to illustrate my point. But I'm going to show you a very simple way of approaching this. So what I'm going to do is I'm going to pick C is equal to, let's try 6. Now you might ask, Dan, why would you pick 6? That seems like a really magical number to throw at me. Okay, so I'm going to lay out kind of the reasoning behind what I'm going to do. So first, I'm going to rely on your assumption about counting, okay? So at the end of the day, once I plug in 6 as the constant here, all I have to do is figure out what n0 should be. And any number that is the one I'm thinking of or greater will work for the selection of n0. So what I'm going to do is I'm going to try to make it so that I end up with, so keep in mind, this will be 6n here, but I would like it to be like n plus 5n, so that I could kind of say, okay, well, I have a 5 over here. I could compare that against the 5n. If you take the n, you could compare that against n. So I definitely see somebody getting onto the idea very quickly. I like this. I like this. So here's sort of the idea, and I usually like to explain this using buckets. So actually, let me write out what the next sentence is going to be so that we know what we're going to be doing. Then I'll justify it in words here. So then we need to find n0 so that for all n greater or equal to n0, n plus 5 is less than or equal to 6n. So, like I said, notice that n plus 5 is going to be less than or equal to n plus 5n, which is equal to 6n, right? Remember, this is the right-hand side of my inequality. 6n for all n greater or equal to 1 as, now you might say, Dan, where did this come from? This seems a little bit like magic, but let me assure you. Okay, so what I'm going to do is I'm going to compare, I deliberately wrote it out like this, so you can see what I'm going to do here. Now I'm going to take advantage of a property that inequalities have. So if I had an inequality that told me that n is less than or equal to n, you'd agree with me that n is less than or equal to n, right? And that has to be true for all n greater or equal to 1, right? Because they're just equal to each other, right? So I want you to imagine that I have, here's a term of n here, and this other one is a term that is my n over here. So I have two n's right here, one on the left-hand side, one on the right-hand side. I'm going to put them into my buckets over here. So I have an n term in each one. So now, if I were to consider now this 5 versus the 5n, you'd agree with me probably that 5 is less or equal to 5n for all n greater or equal to 1, right? This is because if I divide both sides of the inequality by 5, I end up with n is greater or equal to 1, right? You could justify it that way if you like, but it seems rather straightforward. I don't like to say things are obvious. That's usually not something you have to be careful about. But most certainly, I just want to illustrate a point to you. So if I pretend that I have 5 n's over here, and I have the 5's here. So I have, let's see, 1, 2, 3, 4, 5. I have 5 n's right here. I'm going to put that into my right bucket over here. So now I should have 6n in here. There's six of these bottles in here. Now, if I were to look at my left bucket, if I pretended that 5 was 5n, which, so now I have 1, 2, 3, 4, 5. I have 5 here. I'm going to put them into my left bucket. Now, if you look at my left bucket versus my right bucket, would you agree with me that everything in the left bucket is going to be at least what's ever in the right bucket? That's what we're doing here. So notice that if I compare the first term against the first term, and then I compare the second term against the second term, and then what I do is I add everything on the left side, and I add everything on the right side, then most certainly it has to be true over the entire inequality. So that's what we're going to do here. So as n is less than or equal to n, for all n greater or equal to 1, as I take the buckets with me, n is less than or equal to n for all n greater or equal to 1, and 5 is less than or equal to 5n for all n greater or equal to 1. Now I must stress that the reason why we could do this is because notice that I have one inequality here and one inequality here. All I'm doing is I'm summing over those two inequalities. So I take this one and I add it to this one and I end up with that over there. Wow, right? So that's where it comes from. So notice that one, I explained the connection between the left-hand side and the right-hand side, and I gave my reason why. And that reason tells me exactly where this comes from. Does everybody see that? So all it is just collecting things up in buckets and comparing them. So it's really nice and straightforward. At least I think it is. You'll see that there's going to be plenty of examples of these. So now that I have this, can somebody tell me what n0 should be? Or at least some value for n0. Yeah. So notice that this statement that I wrote over here is true for all n greater or equal to 1. This is because both of these inequalities is true for n is greater or equal to 1. If, for example, one of these two statements was true for n is greater or equal to 3, which it is also, but we want to usually write out it in the simplest way we can. You would write that, oh yeah, well, this had to be true for n is greater or equal to 3 because it's over two statements like this. You pick the bigger one. So, very good, very good. So what we're going to do is we're just going to choose n0 to be 1. And like I said, it's okay if you pick n0 to be 2 or 3. You just want it to be very natural to argue, okay? So now that I have c and n0, and I derived essentially how you get them, I'm going to say, therefore, by the definition of big O, as I'm like absolutely taking these buckets with me, therefore, by the definition of big O, n plus 5 is big O of n, right? And that is the end of the proof. That's it. So you might ask, Dan, are there some other constants that work? And yes, there are. For example, in the notes, I believe I give the same example again, but I use two different constants. For example, another pair that you could try. I think you could try c is 2 and n0 being 5, I think. I think those might work. But you'll see that this approach, this bucketing approach, will be very easy to generalize. So, are there any questions about this example here? Is there anything at all that you have questions about? So remember, the goal is to find those two constants, c and n0, and your job is to explain how they work. So you got to make sure that you justify why. So, so if I wanted to say that, so just, can you reiterate that again? So I heard something about being n is equal to 1. Yes. Okay, so keep in mind, remember the goal is to establish the definition of big O. So our goal is to get these two constants. And now when we talk about n0 here, remember n0 has a very special role in this definition. It's that this inequality has to remain true such that this is the case. So it's not just that, oh yeah, if I just like plugged in n as 1 and that's good enough. That's not good enough. Notice that I'm actually arguing why this inequality is actually true. I'm not just plugging in a number. So notice here that when I say, okay, when I chose n0 to be 1 because, like I said previously, notice that I argued that this inequality over there is true for all n greater or equal to 1. So notice, just like in my example where I plotted the two functions out, I found where their last intersection point was. This is just like that. So I found a point where n0 can be established, but any value beyond that could have worked too. But notice that the reason why I pick n is greater or equal to 1 is because this inequality works for n is greater or equal to 1, and this inequality works for n is greater or equal to 1, and I just added over both of these inequalities. Yeah, no worries, no worries. So, that being said, what we're going to do is, because I'm looking at the time now, I know I have some more examples in the notes for doing this, so we're going to have to stop here just because of the time. When we come back, we'll look at some more examples. In particular, we'll look at how we could prove something is not big O of a given function. And we'll talk about proofs for big O as well. I may consider trying to push the deadline for the first assignment because we need some more time to cover this. Would that be okay with everybody, by moving the deadline for the first assignment just a little bit? Because I want to make sure you have some time to play around with the second problem. Okay. Now that sounds good with everybody. So we're going to stop right here. We'll come back to this on Tuesday, okay, everybody? So I'll make an announcement when we do that, okay? So I say thank you very much, and have yourself a beautiful day.